Arratsaldeon guztioi, lehenik eta behin, eskerrik asko Donostia International Physics Centerari eta eskerrik asko ere bai Pedro Miguel Etxenikeri ekitaldi hau antolatzeagatik. Egia esan, ez da makala gure hiriburuetan hain jente bikaina izatea gure artean, gure herrialdeetan. Luzuzko aukera dauzkagu, beraien ezagutzaz, gozatzeko eta beraien ekarpena baliogarri izan dedila guretzako. Ohore handiz gustatuko litzaidake aurkeztea Dame Jocelyn Bell Burnell. En 1968, Nature publicó que se había conseguido medir una radiación muy particular proveniente del espacio estelar que podría haber sido producida por otra forma de vida inteligente. Inmediatamente, los medios de comunicación fueron conscientes de que se trataba del descubrimiento del año, pero cuando se advirtió que en el descubrimiento estaba involucrada una estudiante de doctorado joven y atractiva, los periodistas se dirigieron en masa directamente hacia ella. Le fotografiaron sentada, de pie, analizando datos, escribiendo ecuaciones. Uno de ellos se atrevió a preguntarle si era más o menos alta que la princesa Margarita, a lo que ella contestó: entiendo que en el Reino Unido tenemos unidades de medida muy estrafalarias. La respuesta a la pregunta sobre si tenía novio en aquella época no me atrevo a contestar aquí. Susan Jocelyn nació en Belfast, creció en solitud. El nombre de su casa de campo, junto con sus 3 hermanos y sus padres. Su padre era arquitecto y ayudó a ampliar el observatorio de Armagh, con lo que Jocelyn pasó su infancia rodeada de libros de astronomía. A los 11 años suspendió su examen de acceso a la escuela, pero al haberlo hecho demasiado joven, sus padres, fieles a las costumbres cuáqueras, decidieron darle una segunda oportunidad y esta vez lo superó. Estudió en el Moon School for Quaker Girls en York y posteriormente prosiguió los estudios superiores en la Universidad de Glasgow. Después de su graduación en Ciencias Naturales en 1965, se trasladó a Cambridge, donde realizó su doctorado bajo la supervisión de Tony Hewish, uno de los primeros premios Nobel en el área de la astrofísica. Su proyecto de doctorado consistía en construir un radiotelescopio para estudiar los recientemente descubiertos cuásares. Miss Bell construyó este radiotelescopio a mano y lo dotó de una resolución asombrosa. De forma concienzuda, analizaba a mano todos los datos. El 28 de noviembre de 1968 midió por primera vez una radiación muy leve de una periodicidad terriblemente precisa. Aunque en un principio se consideró que podría provenir de vida inteligente interplanetaria, fue ella misma la que, perseverando en sus medidas, descartó esa idea, ya que consiguió medir esa radiación desde un ángulo distinto del mapa estelar. Esa radiación es lo que hoy se conoce como pulsars, y se trata de una estrella de neutrones que gira sobre sí misma, de manera que son los únicos objetos donde la materia puede ser observada a nivel nuclear. El más famoso de todos los púlsares es quizás el que se encuentra en el centro de la nebulosa del Cangrejo. Este púlsar se encuentra en el mismo punto en el que astrónomos chinos registraron una brillante supernova en el año 1054 y permite establecer la relación entre supernova y estrellas de neutrones, a saber que esta es remanente de la explosión de aquella. De los resultados de su doctorado salió el artículo en Nature, que dio la vuelta al mundo. Aunque al terminar su doctorado la doctora Bell abandonó la primera línea de investigación para desarrollar una deslumbrante y eficaz carrera horizontal, la dedicación de su marido a la diplomacia la convierte en una especie de nómada. Consigue involucrarse en la investigación de las universidades de las ciudades donde vive y se convierte en una experta en astronomía de rayos gamma, astronomía de rayos X, astronomía de infrarrojos y astronomía submilimetrada. En 1974, Hewish fue galardonado con el Premio Nobel de Física junto con Martin Reid por sus pioneros trabajos en el desarrollo de la radioastrofísica y su papel en el descubrimiento del primer púlsar. Jocelyn Bell no fue reconocida junto a ellos. Esta falta de reconocimiento en su momento produjo mucha decepción en la comunidad científica. En cualquier caso, Jocelyn Bell ha recibido muchos otros premios y reconocimientos, como son la Albert Michelson Medal of the Franklin Institute of Philadelphia en 1973, el Archer Medal of the British Royal Astronomer Society en 1989, el Magaric Premio of the American Philosophical Society en el año 2000 y también se convirtió en Fellow de la Royal Society en el 2003 y en 2007 fue nombrada Dame Commander of the Order of the British Empire. And now, after this short presentation that very simply describes this understanding woman of science who, after seeing the very limited ocean there exists for girls and her time, she tried hard in this world of men where women have contributed to science since the very beginning, although they haven't been recognized for doing so. The woman who, after she learned that physics was a simple thing, made the greatest astronomical discovery of the 20th century, a woman whose career is a clear example of the passion for knowledge. Ladies and gentlemen, please allow to me to introduce now you to Dame Jocelyn Bell Burnell. Thank you very much for your attention.
Thank you for that generous introduction. Thank you, ladies and gentlemen, for being here tonight. I'm on my first visit to the Basque Country, my first visit to Donostia, San Sebastian, and it's fantastic. So thank you to everybody who has made this possible. I want to talk this evening about black holes. This is a little bit different from the talks we have had so far. They are much, much bigger than at the atomic level or the electronic level, but they also have some very interesting properties. I will say, first of all, what black holes are, then talk about how we might see a black hole or not see a black hole. How are they formed? What features, what properties do they have? I'll talk a little bit about white holes and wormholes. And finally, the quantum connection. I'll talk a little bit about Hawking radiation. So what are black holes? Well, they are the vacuum cleaners of space. They suck up anything that gets too close, and they send it down a tube away out the back somewhere. They're places where material is lost from our universe, lost forever. You cannot get it back. So they are the end of matter. They are black. You cannot see them. They are invisible. Black holes is a bit of a nickname, but it's a very good name. So black because you cannot see them, and holes because things fall in and go away, way down, and you don't get them back. And they are made by gravity. The early work on black holes was done by Einstein. It's part of Einstein's theories. How could we see a black hole? Well, it's difficult. It's invisible. An isolated black hole, a black hole on its own, is almost impossible to see. But a black hole that is twinned with another star? Perhaps. Many stars are in pairs, and they dance round each other, held together by their mutual gravity. If one of these is a black hole, like in this diagram, an ordinary star twinned with a black hole, the gravity of the black hole distorts this star, pulls material down onto it, and the material circles around and finally falls in. This material gets very hot and gives out X-rays. So astronomers who work at X-ray wavelengths, X-ray astronomers, can often pick up black holes. Interestingly also, it seems that black holes can also produce jets which come out. So they're sucking in material, but also shooting out two jets. And maybe you can identify it by the jets. Very, very big black holes, millions of times the mass of a star, often are seen because of their jets. Sorry. The first discovered black hole, and one of the nearest, is in our galaxy, is part of the Milky Way. And it's in the constellation of Cygnus, the Swan. So here you see the Swan. It's a constellation that's high in the northern sky, although at this time of year you don't see it. You need to wait. No, at this time of year you do see it. That's right. There's the bright star Deneb making its tail, and a nearly as bright star Albireo making its head. And the X-ray astronomers have found there is a black hole about here. This sketch shows the main stars and where the black hole is. For a long time we tried to explain this away by maybe it's not 2 stars, maybe it's 3 stars, or maybe something else. But gradually we have been forced to admit that there is a black hole here, twinned with another star, and the black hole is about 5 times the mass of our sun. We've found many more since then, and we've also found big ones, in the centers of galaxies. For this slide, we need the lights well down, please, and for the next slide. It is a video clip that I will let run many, many times. Can we get the lights down, please? So as you can see the screen. Each of these colored dots is a star. It's a sequence of photographs. The date is shown up here in the top left. It runs from about 1995 to 2011. And there's something special at this point. Thank you, that's much better with the lights. Maybe now you can see the stars. These photographs are taken with infrared light because in the center of the galaxy it's hard to see with visible light, but the principle is exactly the same. Now, long ago, Isaac Newton taught us that things move in straight lines unless something pulls at them. If there's a force, maybe they change direction. Here, everything, or nearly everything, is moving in curved tracks. Look at this yellow one. It's gone round an ellipse. This green one, that one's curved, this one's curved, this one's curved. If there are professional physicists in the audience, watch this one. It's the only one that does not curve. And I would love an explanation of what that one is doing. It might be a quark star. Everything else is curved, and it's curved because there is a very strong force from this point. There's nothing to be seen here, but it has very strong gravity. It's a black hole. It's a black hole at the center of our galaxy, and its mass is about 4 million times the mass of our sun. That sounds a lot, but compared with other galaxies, this is a tame black hole. In other galaxies, they have masses of hundreds of millions of times the mass of our sun, and they're very active black holes. This one is small and quiet, but just don't go too close. I would not recommend that. On the left-hand side here, we have an optical photograph of a big galaxy, another galaxy. It's called Messier 87, or M87. There's several galaxies in the photograph. That's one, that one, that one. But I want to focus on this one. It has, we can see, a little jet coming out the side. If we look at a much bigger area in the radio, with radio telescopes, radio wavelengths, we see the galaxy here, and we see a big jet coming out, and then the jet runs into the material that there is around, and it makes a mess. And in the other direction, there must also be a jet, and again, we see where the jet runs into the surrounding medium. This is typical of a big active black hole in the center of this galaxy. Jets and the actual black hole at the very center. How do you get a black hole? Well, I'm not going to talk about how you get these very big black holes in the center of galaxies. I'm going to talk about how you get a star-sized, star mass black hole. Because we understand that very clearly. In the galaxy case, we probably know what's happening, but we're not absolutely sure. So, suppose this is you standing on the Earth. Here you are. You throw a ball up in the air, and it comes down again because of the Earth's gravity. If there were more gravity, you could throw the ball up, but not so far, and it comes down again. And if the gravity is even greater, you can hardly get the ball up at all, because the gravity is so strong. Maybe you try throwing the ball faster. Okay, helps a bit. But there's a limit to how fast you could throw a ball. According to physics, you cannot throw a ball faster than the speed of light. So let's think in terms of shining a torchlight up. It could get pulled down. When the gravity gets very great, nothing can escape, not even things traveling at the speed of light. And the light ray from a torch gets pulled down again. At this point, this is a black hole, because no light can get out, nor can any radio waves or X-rays or infrared or ultraviolet or anything. Nothing can get out. It's black. And it's got strong gravity, so it's also a hole. What tends to happen is we have some big, big stars, like the stars in the Pleiades, or maybe Betelgeuse in the constellation of Orion. They're 10, 20, 30 times more massive than our sun. They're producing lots of heat and light. And as the heat and light fights its way out from the center, it gives a pressure. The radiation pressure that we heard about earlier gives a pressure that counteracts gravity. But stars are using fuel. And one day, that big star will run out of fuel. And the amount of heat and light will dim. And gravity begins to win. The star shrinks. If a star shrinks, the gravity at the surface goes up. So the star shrinks some more. And the gravity goes up, so the star shrinks some more. And according to Einstein's theory, the stars will shrink and shrink and shrink right down to zero size, infinite density. Whether it actually goes to zero and infinite density, I don't know. But it certainly gets very, very, very small, with very strong gravity and nothing escaping. So big stars at the end of their lives will become black holes, just because they run out of fuel, they stop shining so much, and gravity makes them shrink and shrink and shrink. An analogy, since we're by the sea. Suppose there is a whirlpool. If a boat goes too close to the whirlpool, it perhaps does not have enough speed to escape. A boat far away from the whirlpool is okay. And there is a crucial distance out where the boat can just escape if it goes at full speed. This crucial radius is what we call the event horizon. Event horizon was a concept that was developed by a German physicist, Karl Schwarzschild, and we sometimes call it the Schwarzschild radius. Interestingly, he did this work during the First World War. He was in the German army, he was an officer at the front, and he did these calculations in some quiet periods at the front. He must have had fantastic concentration to be able to ignore everything going on. How big is an event horizon? How close can you go to a black hole and still escape? The size of the event horizon depends on how massive the body is. You could turn the Earth into a black hole if you could shrink it down to about 9 millimeters, that sort of size. I don't know how you would do that, but if you could squeeze the Earth to that size, it would become a black hole. Or if you could squeeze the Sun down to a size of 3 kilometers, it would become a black hole. The black hole's event horizon, its danger zone, depends on how massive it is, and black holes suck. So as black holes suck more material in, the event horizon gets bigger and bigger, and the danger zone gets bigger and bigger. Sorry. Perhaps at home you have a bed with a good mattress. You put something heavy on the mattress and it makes a little dent, hollow in the mattress. We represent space-time sometimes like the surface of a mattress, and a massive object makes a dent in it. If you put something really, really small and heavy on the mattress, maybe it goes through the mattress, wrecks the mattress. Similarly with space-time. So here is space-time with a mass, maybe the Earth. Here, this little diagram, space-time with the Sun. Next, most compact and heavy, is a kind of star called a white dwarf. It makes a bigger dent. A neutron star, a pulsar, that was mentioned in the introduction, makes really a very big dent. But a black hole punches a hole right through. Things can drop right through space-time and are gone. One of the signs that you're falling into a black hole is that your body gets stretched long and thin. So suppose there's a black hole just down there, and I'm going into it feet first. My body gets stretched. There is a technical term for this. It is called spaghettification, like spaghetti. There is also a very strong gradient of gravity. The force on my feet is a lot stronger than the force on my head, so much so that the spaghetti breaks. And even if I curl up small in a ball, the force on the lower part of my body is so much greater than the force on the top part of my body that my body gets ripped apart. So you don't want to go near a black hole. They're not good for you. After you've been ripped into pieces, the various bits fall into the black hole. the atoms get squashed. No longer do you have a nucleus with electrons around it. The electrons get squashed into the nucleus, and then the nucleus gets squashed. Everything gets squashed, unrecognizable, out of existence, in a sense. If something falls into a black hole, it gets squashed, and we have almost no information about what it was. We can know the mass of it, we can know if it had an electric charge, and we can know if it was spinning. But all other features are lost. So we could have the whole Earth fall into a black hole, and all that would be left would be knowledge of its mass, its electric charge, if it has any, and its rotation. Animals, buildings, tools, roses. In Britain, we have a poem about how a rose is forever a rose. With a black hole, a rose is not always a rose, and you cannot smell it, because smell does not get out of a black hole. So there is a loss of information which concerns a number of scientists. We heard in the first talk today about clocks, about how gravity affects clocks, and about GPS. I've got a little bit of the same. I have a crazy cartoon. It's good physics, it's just exaggerated. You see two people, a man higher up with a clock, a man standing on the ground with a watch. The clock higher up is ahead of the watch, because higher up there is less gravity. Clocks go faster with less gravity. Lots of gravity make clocks go slower. So your GPS uses clocks in satellites. Those clocks go faster than clocks down here. This is all part of Einstein's general relativity. And your GPS has to correct for the fact that the clock here is in higher gravity and going slower than the clock in the satellite. Otherwise, it would have you in the wrong position. So your GPS knows general relativity. If you're falling into a black hole, you're going into an environment where the gravity is stronger and stronger and stronger. So clocks behave in a very peculiar way. Suppose I'm falling into a black hole. I have a big watch. You stay here on Earth with a big telescope, and you watch my watch as I fall into the black hole. You see, as I get nearer and nearer the black hole, that I am dimmer, fainter, redder, but also that my watch is going slower and slower. And as I cross the event horizon, as I enter the danger zone, it seems that my watch has paused. I, as I fall into the black hole, can see the whole of the future. It reels before me, but it's not much use because I'm falling into a black hole. Einstein's equations also allow time to be reversed, and as well as black holes, they predict the opposite, called white holes. White holes are places where things suddenly appear out of nowhere. And it's all sorts of things that could appear. Encyclopedias, Pedro, buses, butterflies, or a load of rubbish. It's quite unpredictable because the only information you have beforehand is the mass, the spin, and the electric charge. However, I have to say that we have not yet seen any white holes. but it does open ideas for science fiction writers. Here we have a black hole. Here we have a white hole. Could they be joined by a wormhole or a space-time bridge? Could you go down a black hole here tonight and come up a white hole somewhere else some other time? Maybe some other universe. Fantastic idea. There are actually a couple of problems with this. One is there is a suggestion that when you go through a wormhole, when anything goes through a wormhole, the hole collapses, the tube collapses, and you can't get through. People are saying, well, maybe if you make it spin, it'll be okay, but there is some doubt. The other thing is I want to warn you about. You go into the black hole as a human being. Your body is pulled apart, and as you come out the white hole, there's reconstruction. But it might not be reconstruction as a person. It might not be reconstruction as you. You could go into the black hole as a person and come out as a pig. So be careful what you wish for. And finally, a few minutes about the quantum aspect. You've probably already decided that black holes are really peculiar. And if you had also decided that quantum physics was peculiar, you would not be alone. This bit of the talk is going to be doubly peculiar because it's quantum and black holes. And I'm explaining to you work by the British astrophysicist Stephen Hawking. He's the man with motor neuron disease, and he's been in a wheelchair for many, many years. And it was predicted that he would die 30, 40 years ago, and he's still with us. He's a superb scientist, and I think he's done as much for disabled people as well, just by being Stephen Hawking. One of the elements of quantum physics is due to a German physicist called Werner Heisenberg, who discovered what's known as the uncertainty principle. And one bit of the uncertainty principle concerns energy. It says you can borrow some energy. You can borrow it for a little while, and then you have to pay it back. If you borrow a little bit of energy, you can keep it for longer. If you borrow a lot of energy, you're going to have to pay it back sooner. But you can borrow some energy for a short time. So let's borrow some energy for a short time. With that energy, you can make a pair of particles, strictly speaking, virtual particles. And they can exist, but when the payback time comes, the particles have to combine and the energy is given back. So here we have a pair of particles created. They exist till here, and then they join up again. You get the energy back. And this, we believe, is happening all the time in nature. It's just we can't see it, but we think it is going on all the time. That's fine. But if this is happening near a black hole, then some very interesting things happen. So here we have it again. Borrow some energy, make a pair of particles, join them back again, repay the energy. Here we have it, but there's a black hole here. Here's the event horizon, the edge of the danger zone. You create the pair of particles, and one of them falls into the black hole. The other one is left solo. You can't repay. Nature cannot repay the energy. This particle that's left on its own becomes a real particle. It gets its mass from the black hole. It takes something from the black hole to become a real solid particle. And it goes whizzing off into space. And to us, it looks as if it's coming from the black hole. There's a particle arriving, the black hole has got lighter, it's come from the black hole. This is what Stephen Hawking predicted that we should see. We should see some things coming from black holes. And because the black hole has got a little bit lighter, it's marginally easier next time for this process to happen again, which makes the black hole a bit lighter still, which makes it slightly easier again for it to happen, which makes the black hole lighter, which makes it easier. And gradually, the black hole evaporates, gives out particles like this. Very, very small black holes created at the beginning of the universe have probably now totally evaporated. But ones that are about planet mass should be evaporating about now. And every so often somebody tries to see if they can see them. But it's very, very faint. And as yet, we have not seen an evaporating black hole. This emission of particles is called Hawking radiation, and I think this slide probably says all the things I have already said. One of the pair falls in, the other appears to be coming from the black hole. It's called Hawking radiation. Smaller black holes emit more, and we haven't, unfortunately, sadly, yet seen one. But you never know. The theory seems okay. It would just be good to actually get some confirmation. So there are lots of amazing things happening in and around black holes. Sure, they are dangerous, but they're also wonderfully fun things to study. Thank you for your interest.